It's a great pleasure to have Nikolay Grantcharov speaking about non-abelian Poincare duality and the contractibility in the space of rational maps.
Thank you for the introduction. And yeah, I'd like to also thank Kevin and Justin for help in preparation of this lecture. Not having possible without their help. So yeah, I'm going to sort of explain a series of 5 reduction steps in proving non-abelian Poincare duality to reducing it to some very concrete explicit statement about contractibility of rational maps. And yeah, and this proof that I'll discuss is due to Drinfeld. Okay, so let's recall the setup. So I'm going to work with K in algebraically closed field. And X can be a smooth projected curve over K, and G will be a group scheme over X, smooth and affine. And I'm going to immediately just impose the restriction, since this is the only case we actually care about, that it has generically it has a semi-simple, simply connected fiber. And later we'll actually just see that you can reduce the case where G is like a split group scheme over X. So you may as well just think G itself is defined over K, and it's semi-simple and simply connected. Okay, so now what is non-abelian Poincare duality? It's a theorem which relates the homology of BunG to the homology of the BD Grassmannian. And you should think that the homology of BD Grassmannian is something more tangible. It's easier to work with. And let me recall the definition of the BD Grassmannian. So it's a pre-stack. So which I'll denote by burst of G comma ran. And what it does is takes a test affine scheme S, and outputs the collection of 3 pieces of data. So the first piece is it gives a principal G bundle. Over the curve times S. Second, it specifies a point of the Ron space. So it gives a collection of finite non-empty set of maps. F1 Fn from S to X. And third, it gives a trivialization of the bundle P, so I'll call this P, away from the graphs of these functions. So this gamma sub F denotes the graph. And of course, this BD Grassmannian comes equipped with 2 forgetful maps. So I'll write down here. So Gertrude, Ron, you can think of it as a free stack over Ron. Or you can think of it as a free stack over BunG. And I'll denote this mapped by row. So these are both forgetful maps. And the main theorem, so the non-abelian Poincare duality, asserts that the l-adic homology of the BD Grassmannian is equal to the l-adic homology of BunG. And in fact, the map induced by them is given by this forgetful map. So I'll write it down and pull that. So suppose G has a same symbol and simply connected generic fiber. Then the forgetful map rho from Grantcharov to BunG induces an isomorphism on l-adic homology. And I'll put this in a box. Okay, so here is the main theorem. Now, I will remind you what it means to take l-adic homology in general in the setting of these free stacks. And I will also now proceed by explaining how to prove this. So, all right, let's move on to section l-adic homology. So I'll very quickly remind how one does this because I think we've seen it a couple of times, but it's always nice to have. So suppose Y is a free stack with the presentation that you can write it as a co-limit. Where these straight Y sub i's are schemes. And this curly S is some just indexing category. And now if we suppose that the transition maps to this co-limit are closed embeddings, then we call Y an ind-scheme.
Yeah. So I know only a classical Poincaré duality. Then Poincaré duality says that something is the dual of something. But I cannot see any duality. But why is that Poincaré duality?
Yeah, Kevin, do you know the answer to this? Yeah, that's a great question, and I also wanted to understand this too when I prepared. Okay, maybe during the
I guess maybe one sort of comment. I guess classical Poincaré duality is about sort of compactly supported cohomology and maybe ordinary homology. And I think in sort of Lurie's notes, where he is talking about non-abelian Poincaré duality, he sort of talks about the fact that in non-abelian Poincaré duality, he's sort of replacing homology with homotopy groups. And then trying to figure out what the analog of compactly supported cohomology is sort of difficult for him. And I think more or less the statement of non-abelian Poincare duality is that there's something else that you can use to sort of understand these homotopy groups. And so I'm not sure if there's as much like a direct duality anymore, as it's just this thing that sort of generalizes classical homology can be computed in a slightly different way.
Yeah, there's about 10 lectures of Lurie on topic of non-abelian, and he reduces it to this statement, but it's after a long period of.
Yeah, so for our purposes, for the topic this quarter, we want to understand the homology of BunG, and the idea is that this theorem allows us to reduce it to something local in nature. Okay. So, right, and yeah, let me just make a comment, I'll not write it down. So I defined to you an in scheme, and there's actually like a slightly relaxed version of this where instead of requiring transition maps to be close invariants, you just require them to be proper. Then you get a pseudo in scheme, and that's actually the correct notion which captures the stacks we're working with, like the Ron space and the Ron mapping stack. So if you want to be really precise, you would write down pseudo in schemes everywhere, but we will try to keep notions as simple as possible. Okay, and then, so given in scheme Y, we can define a category of sheaves on Y to just be sort of a limit of the category of sheaves on each of these Y sub i's. And the limit is taken. So I'll write down some words which look scary. So taken with respect to tree pullback. And in the stable infinity. So we don't need to worry about all this. Okay, and now we have a good notion of sheaves on a stack, and this gives us a good notion of homology. So we just defined our homology by taking this co-limit of compactly supported global sections. So this should be interpreted as the derived. And omega sub y is the canonically defined dualization. And here I can actually define what the transition maps, and I think it is nice to have everything down. So let me explain it. So this just means and P is the projectile point. So this just means you take the functor of compactly supported velocity. Let me just briefly explain what the transition maps are in this definition for homology. So transition maps. So in this co-limit are, so given some morphism between two affine schemes S and T, so this would be like Y sub I, Y sub J. You know that the sheaf pullback of the canonical sheaf of T is the canonical sheaf of S. And then using this, you can look at the coordinate map between the Schrieg upper star, lower star adjunction. and then take the compactly supported global sections. So we get an induced map from gamma sub c of f over 3 omega s. And these are the transition maps that are needed to define this object. And now there's a very nice, so if you want even more sophisticated language, there's a very nice diagram which captures this definition, and it's called taking the left con extension, which I'll just briefly summarize. So in summary, what we have is sort of, we're given a well-defined notion of homology on affine schemes. And then we have Bayonetta an embedding of affine schemes into prestacks. And then this induced map is like what we will define as homology for a prestack, and this is due to left con extension. It's exactly just saying that to define homology of a prestack of an in scheme, you just take the coordinate of homologies of each sort of filtered component. And we're going to use this to compute homology of BunG and GURG. Like we will give a sort of nice filtered coordinate by a closed strata and look at each.
Just a quick, maybe a side comment, I'm not sure what I'm saying here. The problem with BunG is not an in scheme, right? A BunG is sort of an open filtration of substacks, whereas GURG is a properly speaking an in scheme. So I suppose the computation of this in terms of closed transition maps probably only exists at the level of GURG, right?
That's correct. That's exactly correct. So the definition I gave really works for spaces which have Ron in the subscript. For BunG, I mean, I want to say it mimics this idea.
Sure, but yeah, I guess that goes back to the first quarter of the BunG stuff.
Yeah. Okay, so that's all I wanted to say about this general nonsense. Now I want to begin with actually like exploring what this theorem is providing us. So just before I give the proof sketch, let me say like one immediate corollary of this, which is sort of already pretty satisfying. Well, as a corollary, you can compute all the fibers of the homology. So we know that the homology by the theorem is the homology of Grantcharov. And then we know sort of by definition my diagram. Well, you have the forgetful map from GURG to Ron given by phi. And this is a very simple object. So notice that the underlying space, Ron X, does not see the group G. Here, there's a G. So here it's much simpler. And then notice sort of the corresponding coefficients, that's only capturing the local behavior. Like, remember that there's this uniformization theorem that BunG like lives over BunG, and this captures like the local behavior. So studying this object really depends locally on G. So it's like a very easy to understand object. And for example, we can look at the fibers. So let's X be some element of Ron X. So this is a finite subset of X. And then we know that the pre-image under 5 is going to be just products of the affine Grassmannian. So I have n distinct points on the BD Grassmannian. And the fiber is just going to be n copies of the affine Grassmannian. And this tells us immediately that sort of this fiber is going to be just tensor products of compactly supported global sections over each affine Grassmannian. So this means the fiber of homology BunG at this subset. So we have some very explicit formula for that. So this is just one application. Non-abelian Poincare.
How does non-abelian Poincare duality
Mhm.
being an isomorphism of homology with ZL coefficients lie isomorphism with coefficients in the dualizing shift?
I want to say it's just, it comes from like the definition of how we give the definition of homology, sort of. I phrased it with coefficients in ZL, but I think I could equally have said it with coefficients in here.
There's some universal
Really,
code.
really means homology. Really, what you mean here is the same as homology with coefficients in ZL.
Yeah. Yeah, so there's
This
this,
is homology with coefficients in whatever.
yeah,
It's the same thing.
yeah. Yeah. No, there's this confusing point which I make all the time. So it does not make sense to consider like the constant sheaf on like ZL, like the constant sheaf ZL. You have to always consider like the dualizing sheaf.
Yeah.
So yeah, I think you can safely assume anytime I write homology, it's like coefficients in the dualizing object. Okay.
How is this related to product formula?
Ooh.
Same thing or?
This must be equivalent to the product.
I want to say it's the same thing, but I cannot.
But of course, the product formula would have BGs in each.
Yeah.
So yes, so by fashion Poincaré duality. That's what to BG with coefficients.
Okay.
What is Grassmannian GXY, by the way? Just very quick. What is this by?
So BunG Xi, I think of as G of K bracket T xi, sorry, open bracket. Modulo, these are the k points. So this point xi, you take the form of completion, you choose a uniformizer called txi, and then it's like the usual definition of gk mod gpo. So they're all isomorphic to one another. I just want to like emphasize that.
Yeah, or just enforce over the formal list with the trivialization. Same idea.
So just the usual affine Grassmannian. Okay, so in the remaining 30 minutes, for the first half, I'm going to explain 3 reduction steps to reduce it to a statement about contractibility of rational numbers. So first, to check a statement of equivalence of homology, it suffices to check it locally. So I'm going to check the statement on each test affine scheme. It suffices to check. Locally. So given any test affine scheme S, which is a point of BunG, so show, I'm going to construct a fiber square. So merge run lives over BunG with rho. And then we have this S point, which I will call like polygraphic P. Okay, polygraphic P and rho are identical, so let me actually call this pi. This is just specifying G parser. Then you have the fiber product. So it'll be S times 1G per G. And you want to show this induced map. Here, I'll call it pi sub rho.
It's a little hard to see the pi sub rho in that color, but
Sorry, yeah. Show pi sub calligraphic P is homological equivalence. Okay, so to show pi is homological equivalence, just check locally over any affine that this induced map is homological equivalence. And we're going to denote this space by sections of P. Because
Find a subset and choice a section from this subset.
yeah, exactly. Yeah. So a data section P is precisely going to specify like a section of the bundle P together with a trivialization away from finitely many points.
yeah, so it's limited the space of all rational sections.
Exactly.
Okay, now.
Away from pi.
Yes. By definition.
Yeah, and I guess you also have to specify that. Okay. Now we're going to define 2 spaces of rational maps, and both will play a significant role for us. So the first one, so I'll denote it by maps sub run x on the y. So x and y are going to be some arbitrary. I think we just care about schemes. So like x will be our curve and y will be our group. So these are going to be pre-stacks, which assign on a affine scheme S the collection of data of first a point of the Ron space. And second, a rational map from x to y, which is regular away from x. So again, I'll use gamma sub x to denote the graph. Now, I will call this the run mapping stack, and then there's going to be the generic. And this is going to assign for an affine scheme S a map M from U to Y, where U ranges over all dense open subsets of S times X, or equivalently over open subsets of S times X, such that it meets every fiber non-trivially. And furthermore, you identify two maps to be equal if they agree on the intersection. I'll put here sort of like a simple star. I apologize for this won't work. So this says M1 and M2 are identified to be equal if they agree on the intersection. Okay. And this is supposed to sort of capture the generic behavior of maps. Like you don't. So here's the difference between these two spaces. In the Ron mapping stack, you look at rational maps and you specify where they're permitted to have poles. The generic, you don't specify where the
So
poles are.
one's open, one's closed. One's sort of quantifying over open sets, and the other one's quantifying over closed sets in some sense, like.
Kind of, I mean. I guess you can think of it that way.
Yeah, it's not perfect, it's because of, yeah, but
I don't know what it means to say like something.
there's not, yeah, sorry.
Yeah.
Oh, what's the intersection?
Yeah, sorry. Is it okay if I just say that loud?
Yes.
Okay, so M1 from U1 to Y and M2 from U2 to Y are equal if agree on U1 intersect U2.
I'm asking about like U intersect.
So it's saying that you only look at U's which are dense in S times X, which means that the U means every fiber, little s times x. Since x is a curve, it's equivalent to single x. I mean, of course, you can make this definition for any spaces, but we really split just x is a curve, y is the curve. Okay, so as I said, there's a natural forgetful map. Just forget the location of the poles. Sort of lots of the reduction steps we're going to do is going to like look at this interplay between the Ron mapping and the generic mapping. So the so there exists forgetful map. And here comes the first semi-reduction statement. This forgetful map induces homological equivalence. And I'll only give you sort of a heuristic argument for why. So you should think that there's a of this as the following. There's an action of the Ron space on this map sub Ron. And in fact, this action is in quotations transitive. And sort of when you quotient out by this action, you get the generic mapping. So again, I'm just waving my hands here. Okay, but as we'll see in the second half, this Ron space is contractible. So if you quotient out by some contractible group, you will have the same homology. Loosely, this is why they are homologically equivalent. So in fact, because Ron is okay.
Yeah, the fibers of that map aren't exactly Ron space.
They're not
but-
exactly
but
Ron.
they're, yeah,
Very close.
They're acted on by
but yeah, I see what you're saying. It's. If you imagine it's a generic section, there are certain poles that you can't.
Yeah, and here's the first
inherit.
the first gripe of Kevin. They're not acted on by transitively. But
They're not acted on transitively.
Right.
I see.
but you can still make this pseudo heuristic argument into an argument
Sure.
by Lurie lecture 10. It's in the notes.
Sure.
Okay.
No,
So
it's at least plausible. It looks enough like Ron space that.
yeah, I hope I will give you heuristic arguments which are all very plausible. Okay, so we now make 3 reductions. First, if G and P prime are G bundles, then which are isomorphic away from finitely mated points. So for X and elements of Ron. Then so then the sections of P over S, so this will be the projection, induces isom on homology if and only if. Same statement for the P prime. Remember, this is what we're trying to show. So in the first step, I argued we check this induces an isomorphism on homology. Suffice it to consider these projection groups. And I'm saying that if you have two different P's, that one induces an isomorphism if and only if the other one does, assuming that the two P's are isomorphic generic. Okay, so why does this hold? So as we sort of discussed verbally already, so the sections are exactly sort of like the F points of so this space of maps X to P, which are defined like the maps of Ron, but also which are sections. In other words, that they're composite back down to X is infinity. And this is homologically equivalent to the same space where I replaced Ron with generic. For the same reason I argued up here. And again, this means just generic map from X to P, which are in fact sections. Okay, but this only captures the generic behavior of sections. In other words, it's insensitive to replacing X by some open U. See, in the definition, we only look at open subsets. And of course, we started with the assumption that P and P prime agree on some open subset. So this shows the first like interplay between going from Ron mappings to generic. Okay. Good. Let's do the second reduction. Good thing I good thing I looked at yesterday.
Yeah.
Okay. 2. So now this will, I think this is like Aaron's favorite theorem. Every principal G bundle admits a generic trivialization.
Here you do mean in this risky sense.
I mean in the tall sense, which I'll I want to say,
Actually, you're probably false.
yeah,
I see.
actually, yeah, it on some tall cover.
That one is almost logical.
Sorry?
We talked about this almost logical.
No, so you do mean touristic, but you mean there's a difference between S and X, right? It's gonna be where you remove some number of points of X or something. And this is because you're probably gonna be using the semi-simple, whether you have to remove one or more points.
Yeah. So what I want to say about this fact is you replace F by some tall cover S prime. And then on that cover, you can trivialize P. So this is the keyword here to cite is Drinfeld-Simpson. So this is exactly like this is verbatim how it's written in Mintom's lecture notes.
Yes, it's all on S, the risking on X kind of things.
That's that's the correct
Yes.
statement. Yeah, I just wrote that's.
Oh, yeah, yes, I checked perfectly.
Okay, so as a corollary, 1 and 2 is we may assume P is the trivial one. Yeah, I see. Let me give a little bit more words about I'll I see I have a little bit of time, so I'll give a legit proof, which is more than 2 words. So P is trivial over S times X. If there exists a U open such that the projection to S is surjective and P is trivial on U. So this is basically the same statement we wrote down here. It's generic. Okay, and this exists on some let's all cover of S due to Drinfeld-Simpson.
Every G torsor can be obtained by head modifications from trivial torsors.
So this word scares me. I don't know what that means.
The action block space on it.
Okay, and now for the third reduction, I will not prove it, I'll just state it. I stated it before, but let me write it. We may assume G. So in the very beginning, I assumed it has generically semi-simple and simply connected fiber, which you can just assume it's generically split, and I'm going to in fact assume it's split. Split. And another simplification is you need to check this over all affine schemes spec R, but in fact, it suffices just to treat R equals K, the ground field. So in this case, sections of P drift. Remember, I can already assume P is P drift, is exactly the mapping stack. Rational maps from X to G, where G is now thought as a group over little k. So now I will state what we're reduced to showing, and we can take a break. Theorem. So it suffices to show this following theorem. Suppose G is as above, simply connected and semi-simple over K, and X is a smooth
And slit. You want to assume split as well?
Well, here I mean split over X. And here, I just mean it's defined over K. So I just assume it's semi-simple over K.
But I mean, you're assuming a split maximal torus, right? I mean, that's the concept of 3, right?
Probably.
So you can reduce it to the quite, probably by an autologous entrance. I see, sorry, go ahead.
I know all I need is simply connected as semi-simple over K.
I see.
Maybe this, yeah, okay. The next is smooth projected. Curve over K. Then this projection I am hiding behind this board. So maps run from X to G down to spec K, induces an isomorphism on l-adic homology. And yeah, so after the break, we'll give extremely simple proof of this due to Drinfeld. Any questions? All right, so in the first half, we made a long series of reductions to reduce the statement of non-abelian Poincare duality to this very concrete statement that the space of rational maps, taking the Ron version, is homologically trivial. So it has the same topology as a point. Now we're going to prove this using what I hope is very low machinery methods, which I hope is very understandable. Okay, let's first treat the easiest case possible where G is the trivial group. So suppose first that G is E, the trivial. Okay, then now let's understand what this Ron mapping space is. So you have to specify a map from X to E. There's only one such map. And then you also have to keep track of the data of a point of Ron space, where the map is regular. So this is precisely specifying a point of their Ron space. So this maps some Ron of X E is exactly Ron of X. And I'll use this to sort of bridge the notation between Luri's notes and my notes. For Luri, this BD sub Gur, this Gur sub G Ron, he calls Ron sub GX for exactly this. Let's do it. Okay. So, and we are reduced to showing that the homology of the Ron space is concentrated in degree 0, in which case you just pick up the scalars. Okay, let's prove this. So I'll call this, I don't know, yeah. So I'll move over here and so I'll say, okay. Proves that Ron is contractible. And I'm going to omit Ron X to save chalk, because X is going to be implicit everywhere. In fact, this proof does not require X to be a curve.
So random anything, including surfaces.
Right.
Are all good, okay. Probably
I think you just need anything connected.
Yeah.
So exactly, so I'm going to say, so we have X is connected, implies that any power of X is connected. I is like any finite subset. This implies the H0 is the coefficients. Which implies H0 of run is going to be just the limit ZLs, so it's just ZL. So nothing surprising here. Now we're going to show by induction that all higher homologies vanish. So assume here's the induction that all homologies vanish for I between 0 and n. So at 0 we computed it's ZL. But now for I equals 1, 2 up to n minus 1, assume it's 0. And let's V be the vector space of the nth homology. We're going to show V is 0. Okay, so
You probably don't want to assume for 0, right? Because it's just not true.
I don't assume for 0.
Oh, I'm so sorry. Strict versus non-strict.
So by Kunev, the nth homology of Ron times Ron only survives in degrees n times 0 and 0 times n. All other degrees die. Okay, now the key feature of the Ron space is the existence of a multiplication map given by union. So there exists this map M from Ron times Ron to Ron given by union. So I'll give it, so given some K algebra R in a finite subset S, then some K algebra R in a finite subset S prime, we map it to sort of R S union S prime. So giving you the map on the R points or spec R points. And some nice features of the union map is that it's symmetric. S union S prime is S prime union S. So what this means is that on homology, the nth homology, you get a map. I don't know how to call it, just like M bar from V plus V to V. It's a linear map given by two linear maps lambda mu, but the symmetry requires lambda to be mu. Union map is amazing. So you also have this other property that if you compose the diagonal embedding and then multiply, so then you take union, you just get back to the same set. So on homology, what does this tell us? Well, it tells us that 2 lambda v is v. So if you go upstairs, you go V goes to V comma V. And then this goes to 2 lambda V. And downstairs V goes to V. So that's one fact. Now, on the other hand, if you just pick any point, so pick a point on X, you consider the inclusion, so like the spec K maps to run X, this map, and consider the composite I'll denote by F to go Ron to Ron times Ron to Ron, where the second map is again taking union, but the first map I don't take diagonal, I take sort of this constant map, comma, identity. Okay, so a feature of this map is that F squared equals F. If you start with a subset S, then you pick up here like X comma S, and here you pick up S union X. If you do that again, S union X union X, S union X. It's an idempotent. And then on homology, so the same property holds on homology. You have a map from V to V, where it sends a vector V to lambda V. So on homology, the constant map dies, just goes to 0. So you have Ron goes to this copy of Ron identity, and then you do lambda on the M. So V goes to lambda V. So this, now the two properties I have, so I'll call this property star. This property star star. And by the way, in characteristic 2, we're already done. So star implies little v is 0. So and little v was arbitrary. So if you're afraid of characteristic 2, it's actually easier. Okay, and now we just combine these two facts, and the proof follows. So 2 lambda v equals by star star. Yes. So lambda is an idempotent. That's what this tells us. So you can say 2 lambda of lambda v. But you know here that 2 lambda of w is w. This just equals lambda v. This is your w. So lambda v is 0. Now, lambda v is 0 implies 2 lambda v is 0 implies v is 0, and v was arbitrary, so this implies big V is 0. And big V, remember, was our homology. So that's very nice, simple proof of the contractibility of Ron, and this is the original proof due to Beilinson-Drinfeld in their Poincaré algebras, just simplified with language which is understandable.
Is this actually the most efficient proof? Because this doubling trick, obviously you could triple or anything of the others.
I think it's the most efficient. I think you extract the bare minimum to, like, you just need 2 properties.
Yeah.
So the way it's formulated in BD is a little more general. It just assumes you have this property, and then you don't pick a point. But here I just pick a point.
Ah, sure, okay.
Like you can replace Ron with some space which satisfies delta composed with union is identity, and you can relax the condition. But here I can pick a point. Okay. Great. So the Ron space is contracted. Let's now do the general case. So first I'm going to make two more reductions. Okay, now I really do want to use X as a curve. Okay, first is suppose that Y is a filtered colimit of closed subspaces for which the contractibility statement holds on any finite intersection. And for me, I will always use the language contractible to mean homologically equivalent to a point. Then maps from on X to Y is also contractible. Okay. And what is the proof? Well, the proof is sort of this abstract nonsense. The proof.
And here, X, you say X needs to be super.
Here I don't need to assume it's a curve.
Oh, okay.
So you always have a map from the colon. So I is ranging over any finite subset. You have a map from the colimit to the limit. And this map is not a homological equivalence. But the stackification is an equivalence. So these are both pre-stacks. But if you take stackification, it's an isomorphism. Right? And now you use.
Sorry, can we just pause for a moment to think what that actually means, stackification? So I mean, that's sort of presuming that on some open set, the actual functor is equal to the limit, so it probably is obvious.
Here, I will phone a friend. So
Is
we test them.
Yeah. Sorry, I don't mean, yeah, maybe I'll have to think about it on my own time, but that's strange.
Wait, what was the question? It's just
It's hard to suddenly think about how to interpret what the stackification of that space of maps means.
well, I mean, it's just a pre-stack, right? So that any pre-stack has like a sheafification. It's like the universal sheaf or stack that it maps to.
So it probably is almost definitionally true then, right? Because it'll define things to be the colimit over all the.
Yeah, I mean, you can also interpret the left side as the colimit taken in stacks, and then you don't even have to stackify. I mean, it's kind of the same thing.
I see, yeah. Yeah, this is just a functor value set, isn't it?
Yeah, here I'm not using anything specific about X or Y.
Yeah, okay.
Yeah, and then the other ingredient you use is that taking homology is insensitive to stackification. Yeah, and note here I work with generic maps. So I also use that maps gen is the same as maps from. So I formulated for. Okay. The second reduction is that we can apply the first reduction in our setting. Okay, so Y is now going to be a group G, which is semi-simple and simply connected. And I think this is where Aaron's question will be answered. Namely, okay, let me finish this sentence. Thus, we may assume Y is a basic open mathematics. I'll explain both. Okay, so this requires the use of the group decomposition. So there exists an open dense subset of G, where U is the unipotent, T is the torus, and U op is the opposite. Opposite means, okay, so actually you start with the ORL B, you define B op so that the intersection is the torus T, and then U is the unipotent radical of this ORL, so you do that, and then you take the corresponding unipotent for B op. Okay, this is open dense. Now call this space V. And one feature of this decomposition is that U is unipotent, so it's affine. So you can write U as like some affine space. T is a torus, so it's going to be affine minus like this coordinate crossing. So
So here's where you assume split this before, that's right.
probably.
Yeah, so you want to just copy GMs or.
So I want this T to look like this, A affine minus BF. And for example, for GLN, it's going to be like the A to the rank of G minus like x1, x2, xn equals 0. Okay.
The
so-
Grantfield is algebraically closed, right? So there's no, we don't have to talk about split or anything anymore. It's everything split.
Yeah, I
Right.
mean, yeah. that was
I'm
very
so sorry.
first thing, Yeah.
Yeah, so my whole
Yeah,
question from first half was not.
So for me, split means you have a group over the curve X, and then you can like trivialize it as like G0 times X.
I see split over.
Split is kind of,
I see.
split is like an absolute notion, right? It's like if you're a split reductive group, you're actually defined over Z. Everything is base change from any, like from the absolute base, so. Right.
Really absolutely get you now. Sorry, I was a little slow.
Yeah, and yeah, I mean, I said this, but let me just write this down. U equals some affine. And same goes for U now. And then T is like A to the rank of G minus this coordinate cross, like minus determinant equals 0.
So you're saying U and U up are affine spaces,
Yeah,
not just like affine varieties, they're affine.
Oh, yeah,
Yeah.
ANs, you mean actually like.
yeah. Okay, so this explains the second, well, almost. Okay, so then V is this U times T times U op, and then G is quasi-compact. Implies you can find a finite set of translates of V. And then you use that the intersection of these translates will still be like of this form. So you have V itself is of this nice form. And if you look at the intersection with any sort of translate to V, it'll also be of this nice form. And that proves this reduction step. So right, we have the intersection of all these translates are of this nice form. If we can prove the contractibility of maps from X to this result, then we can prove it for the whole space Y. So we're just assumed, we're just reduced to this very simple setting.
Sorry, can you say one more time? What were the hypotheses on the the diagram of yi's? Because I remember you saying something about
I'll push the camera to those.
yeah, like the yi's here are open in Y, right?
Yes.
Okay, cool. Okay, you said closed, I think, so I was just confused.
Oh, I apologize.
Yeah. So the yi's are some opens in Y, and then you just all the kind of
Because it's a
intersection.
finite intersection, yes.
Yeah. Okay, got it. Okay.
Oh, that's a very good point. So this is the
And it's not filtered either, right? I think you said filtered. It's like you have just a union of opens with this condition.
This
Okay.
analog of a good cover, right? In Andre Bay's sense or whatever, like where the intersections are all contractible or something like that, or my why is a union?
Well, I mean, I just, the statement is if I can show the contractibility from X to any finite intersection, that I can show the contractibility from X to the union.
Aaron, I think maybe it's relevant that the colimit diagram at the bottom of the board, right? The colimit over I of maps gen, like those are going to be open embeddings, right? So this is like, it's saying maps from generic maps from X into Y are glued out of the generic maps from X into YI or something. And so, yeah, it's like each of those individually would be contractible, and all of the kind of finite intersections of them will be contractible. So yeah.
Great. And that also makes it really clear why the stackification is sensitive.
Is the simply connecting this used somewhere?
Ooh, I don't think so. In this reduction.
Yes.
I mean, I can't remember the accents, but I just used that there exists a Rukali composition. I don't think you need simply connected.
Okay, but then where is the assumption used in this?
Great question.
I don't think it's probably not necessary at all. I think it's probably true for any reductive group. I mean, like it's definitely true for a torus, for example. So
Yeah.
Yeah, tori definitely not.
Yeah, I mean, I'll write down a statement which does not see the group G. And yeah, I think you don't need simply connected, at least to show the contractibility of Ron. But I'm afraid to say in the previous 3 reductions we did, you can get around. Like to reduce non-abelian Poincare duality to this contractibility of maps of Ron, I think you might have needed simply connected, but I'm not sure. Might be like in the existence of this like generic trivialization. I don't know. Yeah. Okay, so let me write down. One final remark. There's a secret reduction 3, but not used. Which says we may assume X is P1 or even A1. And I can just explain in words to the scope of my understanding. So this just uses this Bay restriction sort of argument. So you have a smooth projected curve X. You can map it to P1, like a finite map to P1. And then you look at the Bay restriction. So it gives you like this adjoint property that Holmes from X to basic open affine is the same as Holmes from Bay restriction. So Holmes from P1 to the Bay restriction, and then you use the fact that like the Bay restriction on basic open affine is going to be like basic open affine generically. But then you use that we're only looking at generic maps. So like sort of these two generics cancel out, which allows you to reduce to this. But yeah, so if you want to make things extremely concrete, you'll have the following theorem, and I'll say this theorem. I mean, it's not Beilinson-Drinfeld, but the proof is. Maps sub run X to an minus bf is homologically contractible.
And here we do assume it's a curve or?
Yeah.
Aha.
Yeah, so in the case of A1 and F is just a point, and N is 1, you have the space of rational maps from A1 to A1. So this is like K of T, like rational polynomial K of T. Okay, so Drinfeld gives you a very easy proof to show that this space is actually contractible in any sense. It's even like topologically contractible, homologically contractible, and this proof actually like it captures both of these. Okay, but we don't need X as A1, so proof. So this is like the most explicit computation. So everything up to now has been reduction, and now we actually write some formulas down. So let U, just to simplify notation, be this complement of a hypersurface. Now I'm going to introduce this intermediary object. So I'll denote it by maps sub run X to an, which generically lands in U.
That says introduce. Sorry. I thought I read that as intro sure or something like that.
Sorry, my fingers are hurting.
That was, you're very good board handwriting, so that was
Okay,
error.
that's the space. Okay, so first it contains maps of run from X to U. And it's contained in maps sub run X to an. And this means so collections of maps X to an, which generically land in U. And this generic is in the same sense as before. So I'll say again verbally, so an S point will be a map of S times X to an, so that there exists a dense open inside S times X, whose image lands in U.
So in particular, the whole, you're borrowing the whole map and just landing in the complement.
Yeah, I only wanted to generically land. Okay, so one feature is that this containment is actually a homological equivalence. And I will omit the proof of this. So I will give you two references. So this is Ulrich's lecture notes, number 16. Drop, I think 6 or 7. We have to read the lecture 16. I mean, of course, he does like very sophisticated language, but I think the proof is there. And then there's another reference, which I'll say this Kevin office hours. So he gave another proof of this, which is they're quite elegant. So what you do is you introduce another object, map sub ron sub ron. So you place ron with ron sub ron. And then you have this same space here. And then you can use like just, you'll have like a triangle, and you'll show that like both this leg and this leg are homological equivalent. One of them follows for the same reason that the Ron space is contractible. I think that's this leg. And then the other one, you just construct a pair of adjoint functors. And you can literally like write down this map both ways. And then if you have a pair of adjoint functors, they're going to give the same homology. So both ways work. And now we're going to use this intermediate object. And let me explicitly like write out the method, what we're going to show. So we show the fibers of this intermediate object. So these are, explain, over on. So this is stack, free stack over on. Are filtered colimits, and here I do mean filtered colimit. You'll see these really are all closed conventions of free stacks which are able to contractible. Okay, so this is some stack fiber over Ron. I will show all the fibers over Ron are contractible. Then, using that Ron itself is contractible, I will get contractibility of upstairs. So this is the approach.
What is A1?
A1 contractible, sorry. So if you have a map from X to Y, to say that the A1 contractible means the map, you have a map A1 times X to Y, where, so at 0 and at 1, you get like the original and the target. So it just, you replace the interval, you replace the unit interval by A1 because the unit interval doesn't make sense in the zero space topology. I had the same question when I was preparing this. Okay, fix a point in the Ron space. And then the fiber that I wrote down here, what's it going to be? It's going to be this map from X minus finite collection. Yeah. So these are going to be maps from X to AN, generically landing in U, which are regular away from finite limit. This fixed point you saw. Okay, and consider, I'm going to now give the filtration. So first I'll give the filtration on AN. So maps with target AN. This will be, now to give a map into AN, is the same as giving an n-tuple of maps to A1. Such that the degree of U of I is less or equal to n, where degree I define to be the order of the pole at x1. So I fix this notion of degree to only capture the behavior at x1. And I'm only bounding the poles at x1. So these UIs have poles that's like x1, xn. And I only say, okay, at the x1 pole, it's bounded by degree. Okay. Now this naturally induces a filtration here given by intersection. So I'll say suffices to show for each n maps from x minus x into an bounded by n, the space I just defined. Intersection with maps landing generically in U. So this, I mean, I can write down a subscript less or equal n here to be defined as this intersection. But this inclusion is homotopic to the constant. Let's call this inclusion by dagger.
Sorry, at the right-hand side there, you say is, oh, I see.
So the right-hand side is copy paste of this.
Yeah, sorry, right. Gotcha.
Sorry,
The inclusion is high. Yeah.
should I rewrite?
No, it's as you wrote is just fine.
Okay. So now before I write down the explicit formula, let me give you like the final ingredients. So this is what we're going to do. We assume we have like sort of like n rational functions which are defined away from a hypersurface, which land away from a hypersurface. And we also have that they all have a bounded order pole at x1 equals 0. So what we're going to do is pick an arbitrary point omega with extremely large degree pole at x1 equals 0 and show that the cone, like this line homotopy, lands away from this hypersurface. Okay, so then we have this cone, we have an induced map from the cone of this diagram into the target. And we use that the cone is contractible to deduce that the target is contractible. Now the proof that the cone is contractible is my single favorite proof of all time. So that's the proof. So now I will explain to you how to cook up this point omega with extremely large pole. And this is like due to this, again, like this remarkable lemma of Drinfeld. Remarkable in the sense that it's like anyone can understand the formulation. So lemma. Suppose you have an n-tuple of functions. One thing sorry. there's one important step I have to mention first. So I'll write it down here. Sorry. This is important hypothesis. By no third normalization, we may assume the hypersurface is monic in Z1. So F is of the form Z1 to the D plus lower order terms in Z1. So, I mean, it's basically something like doing a linear change of variables, so you may rewrite your F in this form. And this is important. Because once you have this formulation of F, you can prove the following lemma. So I erase it for no reason. So suppose you want UN are maps which are regular away from X, landing in AN, are such that the degree of the pole UI is bounded by N for all but the first one. And suppose that they live in the hypersurface. So suppose that F of U1 N equals 0. So if you have bounded poles from 2 to N, and you're in the hypersurface, then your U1 pole is also going to be bounded. Then there exists an N prime depending on N and just the degree of the coefficients of F. And here degree means like in the usual sense. Such that the order of pole at U1 is bounded by N. Okay, very simple lemma. I'll skip the proof.
So that's then there exists.
Okay, so this is like 3-line proof using, like you just plug in U1 here, U1 here, U2, UN. We have like, these are all going to be bounded by some N prime. And then you only need to capture like the degree of Z1 to D minus 1. So that's going to be D minus 1 times the degree of U1. And this is D times the degree of U1. And D minus 1 is 1. So that's the proof. And now we're done. So I can now write down the explicit homotopy. So consider U1 N maps to 1 minus T U1 UN plus T omega 1 0 0 0, where the source is in the left-hand side of dagger. So this U1 UN are maps from X to AN, regular away from little x, bounded pole at x1 equals 0, and which generically land in U. So they don't hit the hypersurface. And omega 1 is chosen so that the degree is bigger than n prime. Okay. Now, I claim that the image of this, so I'll call this like phi t. I claim the image of phi t lands in the right-hand side of that grid. So I claim that the maps land in U generically. So I need to show that they don't hit the hypersurface. Okay? Suppose it does. Then you have that this gives you a root of f. Okay, but the 2 through n coordinates have degree bounded by big N. And the first coordinate has degree bigger than n prime, but that contradicts the lemma. Right? If you have the everything but the first order pole is bounded, then the first one is also bounded. Okay, so then image of phi t lands into the right-hand side of the dagger. And of course, when you set t equal to 1, you have just the constant map. And when t equals to 0, you have the identity map. So you have shown that the inclusion t equals 0 is homotopic to the constant map going to omega. And that concludes the proof. I'll stop there. The reference is private communication with Drinfeld. I wrote up notes which I'll post on the website in like a day. I also sent him my notes to see if he approves them. But yeah, this is like, it's a handwritten note that he sent to Gatescory last year, and then he forwarded that email exchange to me.
Oh, this is not in the one that Beilinson sent us a year ago, or?
So this is the bonus material. So the note that Beilinson sent us contained this lemma, but it didn't contain the proof. And then there's a separate document which contains the proof.
I see, okay. Yeah, there's several handwritten documents.
Yeah, so I should say that the references for this talk, there's 4. So of course, Laurie's lecture notes, it contains everything. Then there's Gatescory's paper on contractibility of ground space, contractibility of rational maps, which, I mean, I don't use directly, but indirectly, like a lot of the ideas are similar. And then there's this geometric Langland's office hours from last year. So there's a lecture January 17th and January 24th, 2023, where Gatescory gave 2 lectures on this topic. And I think, I mean, again, all the ideas were there, but it was a bit difficult for me to like parse entirely. So I tried to like spell out every detail in those lectures. And I think this is like I think everything written here is correct, at least. Yeah, and then I said there's a 4th, I forget what the 4th is. Private communication. Yeah, I'll post the notes.
Any other questions?
Yeah.
The lemma.
Yeah.
I mean, when f is 0, maybe it's
Okay.
0 f.
So if f is 0, you I mean, you have just maps from A1 to A1. And I think that case, it's certainly easy. It's easy to show. I cannot figure out right now if it's like the same case, but are you unhappy with the statement? Maybe it's not true if f is 0.
Well, I'm asking if f is 0, it means it lands outside U.
Well, if f is 0, u equals an. U is the complement to the vanishing of f. U.
Or is it like the pole? Is it zero? Or is it zero and some pole? And then so that is
Yeah, I mean, I guess. Yeah, if f is, yeah, f is like any constant, then you can just treat this case separately. It's basically asking like whether this space K of T is contractible. And I mean, you can write this as like union K of T less or equal D. And I mean, if you just mimic Drinfeld's proof, you're going to deduce that K of T D embeds into K of T D for a D very large. You're going to deduce that this embedding is homotopic to the consonant. And you deduce it exactly using like contraction, homotopic like that. Well, n equals 1. N equals 1, f equals 0. This is like the
But
most.
the ca-
Wait, if that is 0, then use them.
So the camera zoom out to show the entire board? No, the whole board,
You want
all
to-
6 boards.
Here we go.
Yeah.
There's a preset for that.
Because I just got back to my apartment and I saw the very end of Nikolay's talk, and now I want to see the whole. Even
There.
further? Yeah, great, thank you. Screenshot. Nikolay, do a post.
Okay.
Is it in perspective, Mataz? The resolution good?
Yes,
Yeah. So if f is 0, there's nothing to show. Like then v of f is everything, then u is empty. If f is any constant which is not 0, then you want to show this is contractible.
Then use the
Yeah.
the whole thing.
Oh, you can correct A and
Sure.
correct,
Okay.
yeah.
Yeah, you can do
Okay.
it.
The output, okay.
Yeah, but the idea is just really simple. Like you show that there's like this you have these natural inclusion maps. I mean, you can put like less or equal n prime. That's what we showed. It's like you just choose n prime sufficiently large, and then you have that's just homotopic to the constant by construction. So it's cone.
Any other questions, comments, concerns? All right, thanks.